Good morning. Some words in português. It's a pleasure to be here. Eu gostaria de dedicar essa charla a Federico e oxalá que daqui a 60 anos estamos novamente em México para celebrar o 120. Okay, let's go to... I try to explain. I will begin with very basic ideas of the talk, and only to say that it's good. I think it's... So the notion that I explore here is the curvature. So, não se escuta. Okay. So the notion that I start with the classical notion of curvature, of plane curvature, of plane curves. So only to say that the curvature is the variation of angular. I don't have a point to show the things, but it is very the beginning. Only to compare with so the next notion is the osculated circle of the curve. This is we take the family of tangent circle to the curve, and the osculated circle is when the contact is not quadratic, is more degenerated than we expected. So for a small circle in this picture, the yellow region is inside or above the curve gamma, and the blue is below, and the red circle is the osculated circle. So the classical important theorem is that a regular curve, a convex regular curve, has at least 4 vertices. That is the points where the curvature has critical points, the maximum and minimum. The thing that is important that is geometrically distinct points, not multiplicity. It's exactly. So what is the usual proof that I consider this? Because at the middle of the talk, we will see the relation with this notion. So we consider the parameterization of the curve by, suppose that is convex. So we take the parameterization by the support function. So the vertices are the zeros of the function h 3 times derivative plus h plus 1 derivative equal to... Thank you. So the verse of the curve corresponds to the zeros of this function. The important theorem about this is this classical theorem that is Hurwitz, after Arnold Tabachnikov also made the proof of this theorem, that says that in this case the function f is orthogonal to the first harmonic. We take the cosinus, sinus, and so on. And the condition that this f is orthogonal to this family of harmonic function. This is the theorem says that if f is orthogonal to this first harmonic, so we have a lot of zeros, 2 times plus 1, exactly as expected. This theorem is very important to give estimative from below for zero function. So we have, and the proof of 4-vector theorem is follows directly from these theorems, because in this case, this function, the first harmonic of this function is 0. So we apply the theorem, it leads to the 4 versus theorem. So this is an idea to show analytical proof of the 4 vertices. I will consider some preliminaries about the geometry of surface in S3. And when we have an immersion in S3, we have the first fundamental form and the second, and the normal, I take the normal positive unity normal to the immersion by this conjunction. So introduce the asymptotic line that I'm interested is defined in the region where the, not so, it's the down. is in the region where the Gaussian curvature is negative. And what is important here is that in this hyperbolic region, we have a net of asymptotic lines, but we can distinguish locally by we take one family for and we have asymptotic 1 and asymptotic line 2 families. This is a local aspect, but what is the important that if you take the surface orientable, so it's possible to make a distinction between the net. We can choose 1 and 2 to define the asymptotic line. So we have an order. How to obtain this is we need to consider the principal lines and take the cone of the direction of principal lines. So the asymptotic lines bisect. We have the principal lines that are orthogonal. So this is, for example, a positive cone. This is a negative cone. And the asymptotic lines direction is bisects this here. So with this consideration, we can distinguish for asymptotic lines. You have a first family and the second family of asymptotic lines. This is important to obtain the results about the inflection points. So the differential equation of asymptotic lines usually is only the zeros of this quadratic implicit differential equation. So if you need to computate, I show you a lot of computation, but I don't. If you want someone are interested, I can show you after how to do the calculation. But it's a long calculation. You have to consider the second differential form. We calculate with this form. So this is a projective notion, but I consider only in S3. For me, it's more comfortable to state the results in S3. And in order to show the idea behind the main result of this talk, I will make a small digression of I consider first the asymptotic lines in the Clifford torus. So in this case, this parameterization, this special parameterization, the coordinate curves are the asymptotic lines. They are global defined. The hyperbolic region is all the torus. And the asymptotic lines are circles that is called the Villar-Source circles, and also are the geodesics on this torus. All the circles in the class 1-1 of the homology, so it's not the usual. The principal lines are in the other position. We have the torus. Principal lines are like this, and the asymptotic lines are the Villar-Source circles. That is another family of circles inside this torus. A classical family of we have a four web in the torus foliated by principal lines, and asymptotic lines are orthogonal because the Clifford torus is a minimal surface. So we have a global picture. This theorem there says that with a Clifford deformation, we can make all the leaves of the asymptotic lines dense in the torus, both. We destroy so we start with this here, and there are helices, and all the leaves will be dense after a small deformation of the. And how to do this? We consider this. In this case, we have not so. We have the coordinate curves are the asymptotic lines. I take a transversal section simultaneous for both foliations. You can consider the diagonal of this kind of picture, and the deformation is the deformation is this one. I consider deformation in the direction of the normal, and in order to stay in S3, we divide in order. And the normal of the Clifford tori is like this. And after we make the computation, the coefficients, before we have A equal, in the Clifford toris we have A equal to 0, F equal to 1, G equal to 0. So the differential equation is only this. After deformation, we have these big expressions for and take this function h like this. What is important here is that you have the symmetry properties here. And after this, with doing the computation of the Poincare return map, we can show that the rotation number for some epsilon different from 0 will be irrational. So we can do with this special deformation, both foliation have the same rotation number, so, and irrational. So both foliation will be dense in the torus. This kind of perturbation, you see that after you consider almost the same kind of deformation in order to obtain inflection points. So now is the start of the main talk. I begin with this problem, this conjecture by Tabachnikov and V that state that a hyperbolic surface in projective 3 space, that is the quotient of S3 by the asymptotic map, has at least 8 for the generic. There are this word here. There are at 8 quadratic points that I will show what means this. The definition of the quadratic point is the point, we get the surface in S3 or R3, is the point where the quadratic is more, the contact of the quadratic at this point, I take all the quadratics tangent to the surface, and that the quadratic point will be the point when the contact is of high order, that I suppose. So the first lemma, that we take a local chart and take the second jet of H with the direction, the U and V direction will be the asymptotic lines. So this is because if we start, so the asymptotic lines will be tangent to the x at the origin. So the condition in order to the point will be a quadratic point is that the coefficient of U and V of order 3 is 0. A3 is 0 and A03 will be 0. So is I show briefly how to prove this. We take the family of osculating quadrats to the surface, that is the equation 7. After this, we manipulation make the Taylor expansion of this quadratic, and you compare with the surface, with the jato of the equation 6, which we see that exactly the relation that we need to establish to obtain the quadratic point. For S3 is almost the same. I take another more chart of parameterization. And in this expression, the quadratic point also is characterized by the vanish of the 2 coefficients of U3 and V3. How the time is? I think it's only to...
You have 5 more minutes.
5? 10. No more.
10 minutes because we have a delay.
Okay. So another notion that I explore here is the notion of inflection point. This is the point I define as the point with where the asymptotic line has 0 geodesic curvature in S3. So we have usually this point, this kind of point, we have a convex behavior, and the inflection is like the contact of x squared is x. So this is a kind of point with the geodesic curvature is 0. So we expect that to compare the inflection point with the quadratic points. So I show in the next proposition that this notion coincides. And this kind of curves are, this kind of set are called fleck-nodal curves. This is Amoxcalli already gave this name. And Ricardo Uribe also preserved this name for this kind of, we have the inflection points, take all the set of inflection points. For each family, you have the inflection points, and the intersection will be the double inflection point of the immersion. So in this picture, in the left, the inflection are, this is coincident for both foliation, this is disjoint. This is a curve for one foliation for the other. In general, we expect maybe when enclosed set, but usually, generically, we expect that this kind of set will be closed regular curves. The proof is, I skipped this because I think it's not so interesting to compare this moment. The previous results about quadratic point is the following, that near cusp of the Gauss map at the parabolic points of the surface, the flexo-nodal curve, is tangent to the parabolic curve. I show in the picture, the next picture, what is the shows important. And the theorem of Ricardo Uribe says that any hyperbolic disk bounded by a Jordan parabolic curve, there is a other number of quadratic points, so it's not empty. So you have a disk, all the time you have a disk, a hyperbolic disk. I make the picture here. What is the important that this is the fleck-nodal curve for the same family. For the other family, this is the union like this. So the argument is a topological argument that we have this kind of behavior of the behavior of the intersection of the fleck-nodal curves in. So I have two pictures exactly what you say. So what is important is the order. Here for first family, the for inflection 1 is in this position, and inflection 2 in this position. So this is a regular curve, tangent. Oh, it's not. But the distinction between 1 and 2. So what I say in the beginning, the asymptotic lines, you have one family and two families that you can distinguish. This is a main point here to prove this theorem. Now I suppose that you agree with me that the four vertices theorem is a particular case of this situation. In the paper of Valencia V and Tabachnikov, they consider a double periodical function is a system of equations. I write this only to, it appears a lot in this. We have this equation, this system of equation, and the question is, what is the number of intersections of these two curves, H1 and H2? The question is, possible that this set will be empty or not, or generically you have at least 8 points in the intersection of this system of function. For each parameter fixed, we have at least 4 zeros. For fixed v, we have at least 4 zeros. For the whole, we have 4 family. But the global picture is difficult to. I show a theorem of a proposition of the paper of Valencia V and Tabachnikov, say that if you take the spatial function like this, it is homogeneous second order harmonic. For the almost A, B, C, and D, we have at least 32 points in the intersection of these two curves. Another example, take from the paper of. We take the H cosinus and make a small deformation. And you have, in this case, you have 8 points in the intersection. This is a picture that shows the position. Above is the same point as below, so we need to take not the multiplicity of the parameterization. So now I characterize the inflection points with the system of equations. So this equation, the red, is the inflection set for the first one foliation, asymptotic foliation. You have two equations that you can eliminate the variable p in order to obtain the inflection set. And the blue is for the other family, for the second family of asymptotic lines. So I use this. How to obtain this is I skip the proof of this, and I consider again the Clifford torus. Now I take another kind of parameterization, but is the same as before, but I take the notation of Tabachnikov and V, and this proposition only to recall that the asymptotic lines are the circles, and the inflection points of this deformation. I take only the normal deformation of the up here. In this proposition, I make only deformation, and you see that the first approximation of the inflection set is like the system considered by Tabachnikov and V. But I need a more complicated behavior of this. So Tabachnikov in the paper explored only the first approximation of the inflection set, the first order deformation. And this recall the four vertices theorem. It's a kind of double vertices. So I suppose this is the conjecture is because this 4 times 4 is 8. Almost finished. Okay, I will show the 2 minutes. So in order to obtain the result, I need to consider a tangent deformation. So it's not only normal deformation. It's not possible to obtain, at least for the moment. We take a tangent deformation also. We consider two kinds of the deformation. The inflection is like this. Begin with the same asymptotic behavior. This is a long expression only to show that there are expressions to manipulate. And now this kind of function, cosine square, is the same as before when I talk about the double recurrence of lines. So in this case, the inflection 1 and 2 coincides for this spatial deformation. After this, I make another deformation, this phi psi, like this. And the main statement is that with this kind of deformation, we can make the double inflection set empty. We have the two curves that coincide, and with this spatial deformation, this is the important here is that the delta that I can here phi make the two curves coincident, and here we can dislocate one of them. So all the analysis is asymptotic analysis with the implicit function theorem, so a lot of calculation to obtain. I have another family, but I will skip all of this. Another family, not embedded, but immersed family of torus, that also with a spatial deformation, we can also to this theorem with this example take a spatial deformation. We can make the set of double inflection empty also. I have also another, because I don't have notion of the time, I consider also the notion of ridge points, but I skip this. After we can talk about this in the coffee or in the lunch. And to end, I gostaria de dizer muitas graças, muito obrigado. And somebody interested, I can discuss about this. Obrigado, Federico. Obrigado a todo o comitê pela oportunidade de estar em México. Graças.